The ocean covers more than 70% of our planet and is one of Earth's most critical resources. This endless body of water looks clean and untouched, but beneath the surface, plastic is accumulating, fragmenting into pieces small enough to be eaten by marine life and passed back up the food chain. Each year, an estimated 8 to 12 million metric tons of plastic enters the ocean. That's the equivalent of dumping a garbage truck full of plastic into the water every minute. Yet despite the ocean's size, that plastic doesn't disperse randomly. It's guided into the same few places by forces we barely notice. And once it arrives, it almost never leaves. What makes this problem so difficult to grasp is that most of the time, you can't actually see it. When people hear ocean plastic, they often imagine a floating island of trash, but reality is far more subtle. Even though the plastic concentrates, it is still spread across millions of square miles, mixed through the upper layers of the ocean and broken into small fragments. That is exactly what makes the problem so complex. Over time, the ocean carries plastic along invisible paths. The Earth's rotation and global wind patterns create huge, slow-moving circular surface currents called gyres. Around the world, these currents concentrate floating debris into 5 major regions. The most well-known of these is the Great Pacific Garbage Patch, located within the North Pacific Gyre between California and Hawaii. It's the largest accumulation of ocean plastic on Earth, estimated to contain over 100,000 metric tons of debris, a mass equivalent to more than 740 Boeing 777s. These gyres contain a higher concentration of waste than the surrounding ocean, but they don't create a visible trash island. From above, the water looks clean. There are no piles of bottles or floating mats of plastic stretching to the horizon. But when you get into the water, you start to see it. Scattered fragments suspended across the surface and below it, distributed unevenly across vast stretches of ocean. Even in areas where plastic has concentrated, there's no single place you can go to simply scoop it out of the ocean. And time only makes the problem harder. Unlike organic materials like paper or wood, plastic doesn't break down and disappear. As it spends years in the ocean, sunlight and waves fragment it into smaller and smaller pieces known as microplastics. Once plastic reaches that stage, it becomes nearly impossible to recover. Marine life can mistake these fragments for food, and as smaller fish are eaten by larger ones, those plastics move up the food chain, eventually reaching us.
And then it starts to break up into these small but very dangerous pieces. Dangerous because the contents of this dish are the actual stomach contents of a single sea turtle that was found dead in Uruguay.
That's why timing matters. The longer plastic remains in the ocean, the more permanent the damage becomes. For decades, this combination of scale, dispersion, and time led most experts to the same conclusion. Cleaning up the ocean simply wasn't feasible. The problem was too large, too diffuse, and too expensive to tackle. But one Dutch engineer thought differently. On a family trip to Greece, Boyan Slat went scuba diving, expecting to see clear blue water and marine life. Instead, he was appalled to see more plastic bags than fish. When he returned home, a simple question stuck with him. Why can't we just clean this up? As he started digging for answers, he quickly learned that most experts believed ocean cleanup was impossible. Boyan, however, thought otherwise. Instead of stopping at the question, he decided to test it. That decision would eventually lead him to found the Ocean Cleanup, a non-profit created to test whether the idea could actually work. The first question they wanted to answer was whether ocean currents could be used to collect plastic without motors or active propulsion. Their first prototype, dubbed System 001, consisted of a 600-meter U-shaped floating barrier that drifted with wind and current. A 3-meter skirt hung below the surface, preventing plastic from escaping underneath while allowing marine life to safely pass below. After enough plastic was captured, a support vessel would come remove the waste and transport it back to shore for recycling. Designed to last a year, System 001 failed after just 4 months. Stress from drifting in the open ocean caused an 18-meter section to break and detach. The team learned that relying on drift alone wasn't sufficient. The system could collect plastic, but inconsistent speed prevented it from retaining debris long enough for removal. Even with its shortcomings, the system still captured 4 tons of plastic and brought it back to shore. The next year, the Ocean Cleanup released an updated version designed to directly address the failures of System 001. Instead of relying on passive drift alone, System 001B focused on one core problem: maintaining a consistent speed through the water. The team tested two approaches. The first was to slow the system down using a large underwater parachute. Wind would push the system in the same direction as the plastic, while the parachute's drag helped stabilize its speed. The second approach attempted the opposite, speeding the system up by replacing the parachute with buoys. These would still be driven by the wind, but with far less drag. Testing showed that the parachute option produced the most consistent speed. It also required fewer components, reducing the risk of mechanical failure. Speed, however, wasn't the only issue. To address the structural failures seen in System 001, the team reduced the system's length from 600 meters to 150 meters. They also replaced the welded connection between the floating pipe and underwater screen with a sling, reducing stress concentrations in the structure. 2 years later, the team was ready to deploy another full-scale system. System 002 was designed to be the first ocean cleanup system intended for continuous operation, not just experimentation. The goals were clear: keep the system operating long-term and reliably retain plastic once it was captured. While earlier tests showed that speed consistency was critical, the team made a major design pivot. Instead of allowing the system to drift or self-propel, System 002 would be towed between two ships. Towing gave the team full control. They could steer toward areas of higher plastic density, maintain a consistent speed, extract plastic when the system filled, and perform repairs without interrupting operations. Over the first 3 months of deployment, the ocean cleanup removed roughly 63,000 pounds of plastic from the ocean. System 002 worked, but it revealed a new problem. At that rate, cleaning just the Great Pacific Garbage Patch would require more than 50 similar systems operating simultaneously. The cost and logistics of deploying that many ship-towed systems simply didn't scale. So once again, the team went back to the drawing board. With System 03, they took a different approach. At 2,250 meters long, it stretches nearly the height of 3 Burj Khalifas laid end-to-end. Compared to System 002, it has roughly 5 times the plastic collection capacity. That scale matters. From their last deployment, the team learned that the cleanup systems themselves weren't the primary cost driver, the ships towing them were. By building much larger systems, they could collect more plastic with fewer support vessels, dramatically improving efficiency. For the first time, large-scale ocean cleanup became economically viable. That shift was reflected in the naming. Earlier systems carried 2 leading zeros because the team believed it would take hundreds of units to address plastic across all 5 ocean gyres. With System 03, they dropped to 0. The projected number of systems needed fell to under 100. System 03 is the system in use today, and it proved that removing plastic from the open ocean at scale was finally possible. To date, it has removed more than 497,000 kilograms of plastic. But it also led to a broader realization. Even with a system this powerful, recovering plastic from the middle of the ocean is still far more expensive than stopping it earlier. Preventing a bottle from reaching the ocean is cheaper, easier, and cleaner than recovering it years later, thousands of miles offshore. Just as ocean currents concentrate plastic into 5 major gyres, river systems do something similar upstream. Out of more than 3 million rivers worldwide, only about 1,000 are responsible for roughly 80% of the plastic that reaches our oceans. Most of these rivers flow through middle-income countries. High-income nations generally have stronger waste management systems, and low-income nations simply consume less plastic. Pollution, in many ways, is a symptom of economic constraints, not indifference. The people and governments along these rivers care about their waterways, but they often lack the resources to address the problem at scale. These high-polluting rivers are typically located near dense population centers and close to the coastline, which gives plastic a fast path to the sea. Many of the top 20 are found in Asia, where large populations, rapid urban growth, and intense monsoon rains combine to wash huge amounts of mismanaged waste into the ocean. One of the most extreme examples is the Rio Motagua in Guatemala. During the rainy season, Heavy floods wash enormous amounts of mismanaged waste down the river and straight into the Caribbean. At times, the flow is so intense that it forms floating carpets of plastic stretching for miles. Rivers like the Motagua don't just leak plastic, they deliver it in sudden, overwhelming surges. And because no two rivers are the same, the Ocean Cleanup developed a suite of 5 technologies, collectively called Interceptors, designed to handle the different challenges rivers present and to capture plastic before it ever reaches the ocean. River width, depth, flow speed, debris type, seasonality, and even tides all influence how effective a cleanup solution can be. So rather than a one-size-fits-all approach, they've built a family of systems that local communities can adapt to reclaim their waterways. The first river cleanup technology debuted in October 2019, and it was called the Interceptor Original. It operates entirely on solar power and is designed to remove plastic autonomously. Floating barriers guide debris towards the system's opening, where the river's current pushes it onto a conveyor belt. The belt lifts the waste into a shuttle that distributes it across 6 dumpsters. The system can store up to 50 cubic meters of trash before needing to be emptied. When it nears capacity, it automatically sends a text message to a local operator. They bring the barge to shore, empty the containers, and return it to the river to continue collecting. But not every river needs a system that complex. For smaller rivers, the Ocean Cleanup developed the Interceptor Barrier, a simple, floating boom anchored in a U-shape across the mouth of a river. It passively collects debris and holds it in place until it can be removed. To service these barriers, the team created the Interceptor Tender, a small barge equipped with a conveyor belt that scoops up captured plastic and transports it to shore. A single tender can service multiple barriers, reducing the cost per site. In shallow gullies, wind and waves can scatter debris outside the tender's reach. To solve this, they developed the Interceptor Guard, a secondary containment barrier that keeps waste concentrated in the collection zone. And in rivers exposed to extreme conditions, the challenge becomes structural. To withstand monsoons, floods, and even tsunamis, the team designs the Interceptor Barricade. It uses 2 heavy-duty booms, one upstream to absorb most of the force and capture debris, and a second downstream as a backup, catching anything that escapes during periods of heavy flow or buildup. But over time, the team learned that engineering was only part of the solution. Just as important were the lessons about how to work with the communities along these rivers. Success depended on local ownership, on community leaders and government partners who could operate, maintain, and advocate for these systems long term. Rather than arriving with a preset plan, they began each project with a simple question: how can we help? Today, the Ocean Cleanup has built the world's largest coordinated, river-based plastic mitigation network. With more than 20 interceptors deployed across 9 countries, they've already stopped thousands of tons of waste before it ever reached the ocean. Using this 2-pronged approach, capturing plastic before it enters the ocean, as well as removing the plastic that has already entered the Ocean Cleanup has shown that large-scale cleanup is not only possible, but increasingly effective. What began as a 600-meter passive barrier has now transformed into multi-kilometer systems capable of capturing debris dozens of times faster than before. Every iteration, improved wings, optimized tow speeds, and reinforced screens, has dramatically increased efficiency. Since the first ocean system was deployed, the team has removed 47,000 metric tons of plastic from the ocean. Between 2023 and 2024 alone, their ocean catch rate increased by 78%, a clear sign that the technology continues to improve year after year. Collection is only part of the solution. Every piece of plastic they recover is traced, certified, and recycled, turning waste back into usable material. This creates a circular system where each cleanup helps fund the next. Their first product was a limited run of sunglasses made from plastic collected during System 001B's deployment to the Great Pacific Garbage Patch. All 25,000 pairs were sold, with 100% of the proceeds funding future missions. More recently, the Ocean Cleanup partnered with Kia, integrating recovered ocean plastic directly into vehicle components. They partnered to create a trunk liner for Kia's EV3, proving that environmental wastes can become part of industrial supply chains. And one of their most unusual partnerships came from the band Coldplay. Coldplay supported interceptor projects across Southeast Asia and began showcasing cleanup footage during their live concerts, bringing the mission to millions of their fans. After seeing the success of the ocean cleanup, Coldplay brought up the idea of producing a limited edition vinyl created using plastic that had been intercepted. Producing a high-quality record from recycled plastic was no easy feat, but by working with multiple partners and focusing heavily on quality control, Coldplay was able to create a notebook edition LP for their Moon music record. The record was made up of 70% plastic from river interceptors and 30% recycled bottles from other sources. Together, these efforts show that plastic removed from the environment can be given a second life. And as that circular system continues to grow, each cleanup makes the next one easier, bringing the goal of a cleaner ocean closer to reality. But that progress doesn't happen automatically. It depends on learning what works and what doesn't. To do that, the ocean cleanup built a research layer around its systems. Research expeditions, drones, and automated imaging help map where plastic accumulates and how it moves, feeding real-world data back into system design and deployment decisions. That feedback loop turns every cleanup into information for the next one. The project is now focused on expansion, deploying larger ocean systems, installing more interceptors in more countries, and expanding cleanup operations across every major ocean garbage patch. Their target is to remove 90% of floating ocean plastic by 2040, a milestone that would have seemed impossible just a decade ago, but now feels achievable with continued iteration and support. What makes the ocean cleanup truly innovative isn't any single piece of technology. It's the way they approached an overwhelming problem as an engineering system, testing ideas in the real world, learning from failure, improving what worked, and redesigning what didn't. They didn't wait for the perfect solution. They built imperfect ones, deployed them, and let reality shape the next version. That mindset, treating global challenges as solvable systems rather than abstract tragedies, is what turned an impossible idea into something engineers could actually build. If you want to help the ocean cleanup reach that goal, please consider donating at theoceancleanup.com/donate. Thank you for watching.